Hello, you're listening to a canned recording of my FOSDEM 2017 presentation running classic applications in a confined ecosystem. As the slide says, my name is Larry Price, and I work at Canonical on some of the new and shiny parts of popular Linux-based operating system Ubuntu. In this presentation, I'm here to talk to you about how we run classic apps in a confined ecosystem in Ubuntu. So what exactly do I mean by classic apps? And furthermore, what do I mean by a confined ecosystem? Let's start with a little bit of background. My job focuses on the idea of convergence, running the same Ubuntu on any platform regardless of screen size, computing power, or target user. Convergence has driven us to build a lot of cool software and explore concepts of security and usability from a different perspective. While we want to take advantage of these new architectures and toolchains we've built, we also want to take advantage of the treasure trove of mature, stable software already available in the archives, and we want the use of such software to be seamless for our existing users. A classic application in this context is any application that I can currently install with aptitude, depackage the Software Center, or any other traditional package manager, and then launch directly from the command line or discover through a graphical interface such as Unity Dash via a desktop file. These applications can be terminal-based or graphics-based using X11. These are applications that we've been using for years to make our Linux desktop experience complete. Apps like Firefox, LibreOffice, Clementine, and the GIMP, and games like Super Tux Kart, Pingus, and Zero AD can all be considered classic applications. Without these apps, it would never be Year of the Linux Desktop. Though some classic applications have been migrated to newer packaging systems or newer display servers, this discussion will be focused on those which have yet to be migrated. Classic apps were designed to be installed and used in an unconfined system. The way that applications have been traditionally installed and accessed resources has grown organically alongside the tooling and other parts of system management. Throughout this process, applications can or must access parts of the system they were never meant to access, and malicious software could easily snoop on the private business of other benign apps. This is not only an issue on desktop, where you're likely checking in on the machine once a day, but also a potential threat to internet-enabled devices which are infrequently updated or checked for health issues and may be scattered throughout your home. Dependencies are another issue with classic applications. Typically, applications depend on several other packages, sometimes with version incompatibilities with already installed applications. Worse, sometimes applications need newer versions of upstream packages that aren't available on the system, or similar package versions have different patches on different distros, leaving the application holding back changes until the newer upstream package can become available, which may not be until the distro makes another release. This could be preventing users from running the best version of an application at any given time. On top of that, we also see an increase in the pollution of our root file system. This graphic does a great job of visualizing the traditional way the Linux file system is organized. You may notice that there's a lot going on here, and some of these directories may seem redundant. For instance, all of these directories are in the path environment variable on my development machine, meaning I could have user runnable binaries in bin, sbin, user sbin, user games, user local bin, sbin, and games, and scattered throughout any number of directories in my home directory. Similarly, library and data files appear wherever they please. These are the library search directories I found when running ldconfig. For data directories, I'm honestly not sure I could construct a complete list. So, to generalize the goal of confinement, we want to move away from letting applications snoop on each other without permission, and we want to take back control of our file system, putting these applications in a known location and giving each application the appropriate dependencies. Our traditional package manager and Debian-based operating systems, depackage, is over 20 years old and carries the burden of those years on its shoulders. Because of this, we thought it would be best to introduce a new packaging toolchain. For some history, a couple years ago, Canonical announced click packages. An application packaged as a click is bundled with any specific dependencies and utilizes Ubuntu frameworks for shared resources. Clicks also allow developers to create a confined application using AppArmor to specify any security features it may need. Clicks made headlines for being the de facto packaging method for the initial round of Ubuntu Touch devices. These devices ran Mir instead of X11, as well as Unity 8 as a desktop environment. And with all of that technology in place, we had our confined system, but the system lacked maturity and was missing some important features. More recently, we've seen the emergence of snap packaging, also referred to as snappy. Snappy is essentially a new iteration on clicks, giving better version management, sleeker application confinement definitions, and new ways to interface with other applications. You can use snaps today on modern versions of Ubuntu or several other distributions, alongside the default packaging systems. Snap apps all live in a special root directory and can be completely confined and installed from stable channels, or unconfined when installed from unstable channels. Snap applications come bundled with all their dependencies pulled locally, allowing apps to upgrade their dependencies as needed as opposed to waiting for upstream package maintainers. Snap applications are also automatically updated once a day when updates are available, taking the pressure off the user to ensure apps are up to date. Snaps come with the option for Delta updates, which allows the Snap toolchain to download a diff instead of an entire package, making downloads potentially smaller and faster. And as confinement is concerned, Snap apps are relegated to their read-only piece of the file system by default, requiring interfaces to be connected to perform system tasks such as using the display, writing the home directory, and connecting to the network. When snaps are used in a hybrid or classic environment in addition to a traditional package manager, we can continue to pull in and use classic apps while enjoying confinement and security with our migrated apps. However, one exciting premise of snaps is the ability to run a fully confined operating system using only snaps. But this puts us in a bind. We won't be able to run classic apps in this fully confined ecosystem. Our good old classic apps are expecting an unconfined environment, and they expect to use the X display server, and this all snaps environment is prepared to give them neither. We need a way around this issue to allow users to run classic applications and have a full desktop experience. So we've been working on a suite of tools, which we call Libertine, to resolve this problem. A libertine is a person who acts without moral restraint, living one's life for pleasure while only thinking of oneself. In a sense, our classic applications are practicing libertines, and our goal is to pull them back into moral high standing. These classic applications need a safe place to go wild while the rest of the world falls in line. Libertine creates this safe place as a Linux container. These containers are nearly unrecognizable from a traditional Linux desktop experience. A Libertine container has its own file system to work with and binds to system resource directories on the host system to use things like sound and external media devices. It also binds to the user's home directories to give read-writable access to data. Internally, we continue to use apt and dpackage to manage packages, even if the host system is unable to do so, even if the host system does not have dpackage installed. Libertine connects to instances of Xmirror, a mirror-to-X compatibility layer, to launch X applications in a non-X environment. Every installation, removal, and system modification is done internally, protecting the outside world from these classic applications. The Libertine suite has many parts to abstract away the underlying implementation of classic Ubuntu as best as possible. There's a C++ library and GUI application, Python launchers and command line interfaces, and tools to control other aspects, such as clipboard and launching Xmirror. I'll go over a few of those parts now. The Libertine suite keeps track of all available containers, installed packages, and running operations in a JSON file which it uses as a database. This database is maintained for each user individually on a system stored in the user's home directory. Using JSON for our database file allows us to avoid adding dependencies on database frameworks and allows us to easily ask for the database file when debugging user issues. Our Python library is the crux of our container management. Of course, it contains an abstraction around the database and utility functions, but the heart of the Python library is abstracting away the process of handling different implementations of Libertine containers, of which we currently support 3 types: Chroot, LXC, and LXD. Chroot is a special case maintained only for use on devices with kernels too old to support LXC or LXD. With a Chroot backend, we use the fakeroot command line tool to create a base Debian system in the user's home directory as a Chroot jail, from which we'll use to run all of our commands. When running commands within a chroot, we use a tool called proot. We'll generally run proot unprivileged to run the command from within our chroot jail. But sometimes we need to run privileged proot commands, giving away more control than we'd like, and we consider a chroot container somewhat deprecated, though still useful. LXC containers have been our preferred container type for most of Libertine's lifetime. LXC combines the kernel's C groups and support for isolated namespaces to provide an isolated environment for applications. LXC pulls Ubuntu base images for us to copy into the user's home directory, just as we did for Chroot. We create unprivileged LXC containers, setting up the host user inside the container for appropriate access to home and system directories. Setting up unprivileged LXC to integrate with traditional desktop features can be tricky, and we go to great lengths to ensure the environment is correct and that we can connect to system resources such as audio. I'll also note that the LXC Python API is fairly mature and works relatively well for our needs. For instance, when we execute container commands, we use the LXC container's attach method to run our command within the container. But the newest, shiniest Libertine backend is for LXD containers. LXD is a new face on top of the LXC implementation, simplifying container management and frequently providing speed and usability improvements as well. Libertine LXD containers are outliers in that we depend on the LXD service itself to maintain the root file system, though we still maintain the home directory and applications directories locally. For the most part, setting up a LXD container is very similar to setting up an LXC container. We bind mount several devices and files, map the current host user into the container, and start setting up default packages. LXD also makes it simple to define a Libertine profile, which we share amongst all of our Libertine containers, defining common behavior and mount points. One interesting case study is how we handle /run/user in LXD. /run/user is a system directory for storing files used by running processes. When a LXD container starts, this directory is overwritten completely, but we need to map it directly to the host user's /run/user directory. So to work around this, we create a custom script and copy it into the container. This script creates missing directories, fixes permissions, and remounts things like /run/user to ensure the system is in working order. We add the files to the container using the Python PyLXD files API, and we use the execute command to run the script anytime we start the container. The Python API for LXD is not quite mature enough that we can use it in 100% of our use cases, so we use a hybrid solution of the official Python API and calls to popen to start processes manually. As an example, we use the Python API here to update the list of devices available by default in our Libertine profile. All we need to do is update a dictionary with the values we want. When we're ready, we save the container's configuration, which will let us know there's an issue through LXD exceptions. On the other hand, when we start an application, we use the command line interface instead through a call to psutil.popen. This is currently the only way to run a command in a LXD container in Python and get all the output while the command runs in the background. Launching LXC and LXD containers can be expensive, so we've also written debug services, which are primarily responsible for keeping track of the current state of these types of containers and starting or stopping them appropriately. These services are only accessed from within the Python container classes and only when they are actually available on our system. When several apps are open for a container, this debug service helps ensure that we don't try to shut down a container when any single app stops, but instead wait until all applications have been closed by the user. Keeping containers stopped helps save battery life and lets us refresh bind mounts and LXD profiles liberally. Moving on to binaries that use the Python library, Libertine Container Manager is a command line tool written in Python for users to directly create and manage containers and applications, add multi-arch support, and update bind mounts. This is a basic overview of using Libertine Container Manager to create a container alongside the changes to the database and file system. We use a create command with various flags and options to build our preferred container, and then intelligent defaults are available for everything here except for the container's ID. And this will do any number of things based on container type selected, but the user doesn't need to be privy to the underlying container backend, shown here symbolically as a black box. The database will be updated with our new container its info, and a new root file system is created. And this is an overview of installing packages. Note again that a package name may not line up with the binaries installed, but we're only keeping track of what the user explicitly asks us to install. The purpose of Libertine Container Manager is to prevent the user from having to deal with the low-level concepts of any particular container type or package management system, and instead focus on the simple syntax of creating and installing. We also have a debug service written in Python to replace the work being done by Libertine Container Manager. Many of the commands run by Libertine Container Manager take quite some time, and bad things tend to happen when those commands are interrupted. For instance, stopping dpackage mid-command can lead to broken package installations, which is a situation we'd like to avoid. Libertine D aims to solve that by being a completely asynchronous method of managing containers. The idea here is to launch the exact same logic as we did in Libertine Container Manager in a Python thread, and send updates through dbus signals. Although the container management functionality is available for future use, the primary use of Libertine D today is to list containers, report container paths, and list applications available within containers to external libraries. Our C++ library liblibertine is the root of discovering container information for several external libraries. It's currently a wrapper around a client for Libertine D. Many of the low-level libraries that access Libertine are written in C++, and liblibertine gives convenient access to lists of Libertine containers and applications. In the code sample seen here, you can see the dbus calls being made. We also have a GUI written in C++ with Qt-Quick, which wraps the Libertine Container Manager. This is an easy way to manage containers for most users, even if they're less technical, and abstracts the Libertine Container Manager concepts a bit further. This app is largely a series of lists showing the available containers and the corresponding installed packages. For the most part, functionality in the GUI is on par with that of the command line tool. The GUI is available as a standalone package or as an additional panel in the Ubuntu System Settings app. Launching applications is the responsibility of a separate Python tool called Libertine Launch. Libertine Launch cleans up the environment for running applications and then forwards that environment to the container implementations to actually run the application. Libertine Launch can be used from a terminal, but it's generally launched as another process from application launching tools such as Ubuntu App Launch. Libertine Launch also has a companion binary to help applications use a clipboard. This app will use cute signals and slots to wait for copy or paste events and forward them to or from the base Ubuntu Content Hub. This makes copy and paste work pretty much just like it would in these apps within a classic environment. So what actually happens when we launch a classic application using Libertine? Clicking on a desktop icon calls Libertine Launch with the container ID and application exec line found in the desktop file, which was probably discovered by a call to liblibertine, which discovered the application via Libertine D. Libertine Launch starts utility binaries such as the pasted daemon for clipboard access. It updates the environment and uses the Libertine Python library to create a representation of the container and start the application. The container object does any number of things at this point, including updating the bind mounts and system devices it can access, starting the container, and starting up a window manager process. For LXD and LXC containers, a quick dbus call will be made to determine whether a container needs to be started. At this point, a new window should open running our classic apps. And that's most of the full picture. To review, we build a container using one of the Libertine management tools and set it up to install applications through apt, even when apt isn't on the system. Libertine keeps the container and its classic apps confined to their root file system and the small holes we poke to let them into the host system to use capabilities such as sound and graphics. Someone or something will then launch applications with Libertine Launch, which prepares the container's environment to mirror the host, starts a window manager inside the container connected to the host display, and launches applications. And given all that, where can we actually use Libertine? The answer is, well, in most of our modern Ubuntu systems. Unity 7 is the current default desktop session in Ubuntu. Libertine in Unity 7 is a bit silly, seeing as how Unity 7 is not generally a confined environment, already runs X11, and installs packages with dpackage. However, it's worth noting that Libertine works just as well in this environment and enables users to run classic applications confined within a container. Because Unity 7 is already running X11, Libertine's classic apps can use the running X server to connect to their window manager. But it's not all sunshine and roses, as application Libertine containers do not automatically show up in the Unity 7 dash. In order to launch these apps, users will need to manually run Libertine Launch or create system-findable desktop files. Unity 8 Desktop is a new and improved version of Unity 7, running Mir as its display server instead of X, pre-installed on Ubuntu since last October as a non-default desktop session. Desktop Unity 8 is also not particularly confined, but running Mir instead of X alleviates some of our previous security pains. Mir in Unity 8 can run some applications natively, such as modern Qt apps, but it doesn't have the ability to run all of our classic apps. Libertine works well in Unity 8 and is built into the application discovery logic. Clicking on an icon for a Libertine classic app will end up running Libertine Launch the same way as we saw in Unity 7, but in this case there's no X11, so the system will also start an instance of Xmir for our application to attach to Window Manager 2. Xmir is a way to run an isolated X11 window on top of Mir. Each running Libertine application will then get its own Xmir, preventing unwanted communication between apps. And with this step, we've successfully run X apps in a non-X environment. Ubuntu Touch is similar in that it runs Unity 8 and Mir and therefore cannot run classic apps on its own. Furthermore, users were prevented from using apps or dpackage to install apps due to Ubuntu Touch being a read-only file system by default. So even applications that would work in a desktop Unity 8 environment may not have been installable in Ubuntu Touch. With varying hardware and screen sizes, classic apps don't always run as well on mobile devices, but on some devices, like the BQM10, we would pre-install a Libertine container with some essential classic apps such as LibreOffice and XChat. These apps worked relatively well on a tablet interface and gave us a peek at a truly convergent environment. We use Libertine almost exactly the same way here as we did on Unity 8 Desktop, launching and attaching to an Xmir instance, except that the older kernel on the M10 requires us to use chroot-based containers. Now, our end goal has been to run classic apps in a completely confined ecosystem, which brings us to snaps. As mentioned, snaps are a packaging system to allow complete confinement, and Ubuntu Personal is a system comprised of only snaps. When packaging Libertine as a snap, we build Libertine from source using CMake and create one giant package file. We needed to update some pathing and environment checking to be more flexible for snaps, and we had to make some changes to liblibertine and Libertine D. Snaps also encouraged us to focus on getting Libertine LXD back and up and running, as there's a LXD snap available which we're able to use with Libertine. In order to get Libertine working in a fully confined environment, we need to specify some interfaces. Listed here are things like LXD, which allows us to talk to LXD, the network and network bind interfaces, which allow us to talk to sockets and communicate with the network, the home interface, which allows us to gain access to some directories like downloads, music, videos, and then all the rest of these are used for graphics and sound. Okay, time for a live demo. These things never work though, right? Well, as luck would have it, this version of Firefox is currently running. within a Libertine container, which has been snapped, and I'm also recording this whole talk using Audacity, which has been running in a snap. For further proof, we can look at something like xterm, which comes up. And you can see that things like Firefox are running with the commands that we gave them in LXD. And we can go ahead and just get back to the presentation. To review, we wanted to find a way to run classic desktop apps in a non-classic confined system without a true X11 and using a new packaging format. Libertine allows users to build containers and manage classic apps without the knowledge of container or packaging syntax. We have this working on all of our modern Ubuntu systems to some extent, and it works to make a relatively seamless experience. Of course, the setup works nicely on my machine right now, but we're still working on a lot of stuff. We'd like to have a more seamless installation experience for our users instead of having to use the command line or separate GUI. Dbus is causing some headaches within the snap, especially for a bunch of GNOME applications. Our snap is quite big, which I'd like to address. And that's it for me. Feel free to reach out with any questions on Twitter or Freenode, and you can find all the code for Libertine on Launchpad and all the code for Snap and all of its utilities on GitHub. Thanks for listening.